Professor Saburo Tanaka is from Toyohashi University of Technology from Japan. And the talk, the presentation is entitled High TC Squid Applications for Metallic Contamination Detection in Li-ion battery liquid components. So presentation is online. We see the presenter. Hello, Japan.
Hello.
Can you hear us?
Yes, yes. Okay, I will start. My name is Saburo Tanaka of Toyohashi University of Technology. I'm very happy to share our recent application of high TC scale. And we are cooperating with Nikka Densoku. It's a manufacturer of a metallic contaminant detection system. And today I talk about high TC squid application for metallic contaminant detection in lithium-ion battery liquid components. Okay, and here is the outline. Firstly, I talk about background and objective and experimental setup. Then followed by a sample preparation, and I show you the results and discuss about that. And I conclude my talk. Okay, and with a higher performance due to higher density of lithium-ion batteries, the risk of overheating and fire is increasing. And the technologies for product safety and quality control are becoming important for battery component manufacturers. And we have been developing an RF squid system for detecting a metallic contaminant mixed in the liquid component of a lithium-ion battery slurry, such as a slurry. This is a slurry. And this shows a cross-sectional view of lithium-ion batteries. It consists of a separator, anode, and the cathode electrode. And if there is a contaminant here, it penetrates, separated, and it makes a short circuit. And it becomes sometimes fire or explosion. So contaminant with a size of larger than 10 micrometer becomes a problem. And we should detect that and control that. And we have executed detection experiment using a simulated system without liquid to date. And in the system, we put a metallic contaminant. It's artificially made, and it was stuck on the fishing lines and drawn by motor. And a squid here, and a squid detect the immanent field, magnetic field of magnetic particles. And today, I show you the system, new system, which detects metallic contaminant in flowing water, liquid, in the tube. And this is an overview of the new system. And there's a squid here, and this is called so-called squid microscope type of cryostat. And the water is circulating by a pump. Actually, this is a system for laboratory. So real system should be inserted in the production line of batteries. And we prepare the rectangular trench pipe here. And sample is sucked from here, and it's flow and magnetized by a permanent magnet, and the squid will detect the signal. And this is the detection area. And this shows a close-up view of detection area. And the squid is here. And the trench width is 8 millimeter. And the squid size is 9 millimeter. So it's large enough to detect this direction. And this is a cross-sectional view. So water is flowing from here to the screen side. And the space between the squid and the top of the trench is 1.8 millimeter. And here is the appearance of the system. This is a magnetically shielded cylinder, which preventing from the outer magnetic disturbance. And water flows this way, and squid cluster is installed inside. And these are electronics, oscilloscope and the filter and the computer here. And this is a squid design, RF squid design. This is homemade and we designed and we made. It's a 9 millimeter scale, and there's one junction. It's not DC squid, but RF squid. So one Josephson junction is here. And the squid hole size is 100 micrometer by 100 micrometers. And expected squid inductance was 157, and the effective area, this was 0.4 millimeter. And here shows measure the flux noise. And this is the frequency, and at the white noise level, it's about 40 microfine note. And here, 10 to 100 hertz, it's 50 to 70 microfine note. And it's enough to detect the signal. And here is a sample piece. We made the sample. Now, it's difficult to obtain small metallic sample under dimension of 50 micrometer on the market. So we fabricated samples by using gallium focused ion beam, gallium FIB. And we purchased several wires, stainless steel wire with a different diameter. And we use gallium FIB here like this, and we take out this small piece. And we made finally the sample dimension of 50 micrometer in dia and 50 micrometer length, and 30 by 30, 20 by 30, 3 pieces. And each sample was very small, so sample was molded by plastic resin, preventing from rust. And here shows a signal flow. The signal from squid electronics, it's passed through high pass filter first, and then a low pass filter. The corner frequency of a high pass filter was 10 hertz, and the low pass filter, the corner frequency was 100 hertz. So finally, in here, the signal is passed through a band pass filter from 10 to 100. And the signal was taken by a DAC, data acquisition unit. And here shows a real time trace we obtained. The sample size was a stainless steel sample, and the dimension was 50 micron in dia and 50 micron length. And the flow rate was 33 meter per minute. Now this is a raw data. It's noisy, unfiltered result. And when we apply a filter, it's dramatically improved. So the signal, this signal is the frequency component from 10 to 100 hertz. So this was improved. And the signal to noise ratio, SNR, was dramatically improved. So hereafter, we applied the filters to obtain the signal. And here it's a time tracing for each repetition. We repeated the measurement using the same sample in water flow. So we repeated, but the signal was very variated. You see, this one is no signal, and other was big and small, and you know, the very variations, many variations. And we name this type, this pattern as NPPN. It's a negative, positive peak, and a negative. And here is a reverse, positive, negative peak, positive. So PNPP, like that. And this one is very different from this bedmark signal. It's a negative peak and a positive peak, two peaks. And here, NPPP, you see? And this one is a reversal, PPNP. It's 180 degrees different, phase was different. And here, this one looks like a signal of here, number 4, but the peak size is different. The smaller negative peak and the larger positive peak, it's asymmetric. And we made some expectation. And the waveform shape depends on the orientation of the dipole of the sample in water when detected. And then here is the explanation. Now these waveforms are the same one. And in the case of F, no signal. But this one, number 2 is the dipole direction must be this kind of direction, orientation. It's vertical, you see? And this one, reverse way, it must be the reverse, NS, but this one, SN. And the squid level is here. Squid detection level is here, located here. And this one, negative peak and the positive peak. In the case, it must be horizontal. And also this one, smaller and reverse signal. It must be NS, not the SN. And in the case, it's a little bit far from squid. So in the middle of a trench, it's a flow. And this one, asymmetric signal. It must be rotated, tilted with some angle and close to a squid. The signal peak is large. And this one, small signal must be here in the middle. It's a little bit far from a squid. And this one also smaller. And finally, number 1, it's no signal. In the case, we expect that very far from a squid. It's not a detected level, it's a noise level. And the direction of a magnetic dipole could be roughly divided into 6 categories, A to F. And that could explain all the experimental results. This is the topic of main topic of my talk today. And here shows a dependence of sample diameter. This is the sample diameter, equivalent diameter. This is the signal. And in the case, we indicated the maximum peak. This one was a maximum. I mean, when we measured the peak to peak values variated. Sometimes signal was here, sometimes a 0. But it shows only maximum peaks. And this one scaled with scaled by a cube of diameter. And this means the signal is proportional to the sample volume. It's theoretically correct. And if we suppose threshold level as a signal to noise ratio SNR3, 20 by 30 micrometer small particle could be detected. And here is a dependence on trench depth. Trench depth means from here to here. Here, it's 0. And here, trench depth was 5 millimeter. And when the contaminant flowed here, it's close to a squid. So it's easy to detect and the signal was large. But here, the bottom of the trench, there's a far from the squid and the signal become weak. And we calculated, for example, 50 by 50 sample. At here, the signal is 50 millivolt. It's as I showed a previous view graph. It's the same value, 50. And when the depth becomes deep, the signal decayed. And at the signal to noise ratio equals 3, here it's 2.2 millimeter. So you can detect the sample position at 0 to 2.2. You can detect with signal to noise ratio more than 3. But for smaller one, 30 by 30 micrometer sample, you can detect here, but here is 0.7, maybe from almost the top, but 0.7 millimeter deep, you can detect that. And for smallest one, 20 by 30 sample, you can detect only at the 0 depth. Here, only here, squid can detect the smallest sample, but otherwise, no signal can be taken. So to increase the critical depth, reduce standoff distance, so this 1.8 millimeter between squid and the trench, and lower the SNR level, 3 level, by improving the squid flux noise of the squid. So squid should be improved. And here is a conclusion. Now we developed the inspection system using RF squid for metallic contaminant in lithium-ion battery liquid component. And the time is coming, so I I conclude my talk showing this slide. Thank you.
Thank you. Thank you. A very nice presentation. Are there any questions from the audience? Or maybe there is a question from our online viewers? No. So maybe I will, but it's not really a question. I would say it's just a comment. Will it pay off if you just pay second squid on the other side of this trench and then connect it in such a way that you would actually measure the difference of the signal between these two squids? So then you could have a common noise rejection, and probably you would also increase the sensitivity. So what do you think? Is it feasible, or?
Yeah.
What can you?
Thank you. It's possible. It's one option, we think. And another option is make the trench depth half, 2.5 millimeter. And parallel, put the parallel squid, one more squid here next to the one squid. And there is a two parallel trench is applied. It's possible. But as you mentioned, we can put the bottom side, one more squid. It solves the issue. Okay.
Okay, thank you very much, Professor Tanaka. So I don't see other questions. Thank you once again for your presentation, and we are switching to the next one.